Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry reactions and solutions to homework problems. In this scribblecast lecture, we're going to start taking a look at free radical reactions. We're going to begin looking at free radical reactions in alkane derivatives, then take a close look at oxygen and move on into organometallic reactions. If you react carbon with heat in the presence of oxygen, you get combustion and CO2 gas production. But what happens if you actually react alkanes, carbon-containing molecules, in the presence of heat with no oxygen available? In such a case, you will observe what is referred to as a pyrolysis reaction. Pyrolysis reaction. A pyrolysis reaction is thermal decomposition of an organic compound in the absence of oxygen. So if you like, thermal decomposition of organics. I'll say organics, but I mean organic compounds. And this is very important, in the absence of oxygen. So in the absence of oxygen, let's consider, for example, the molecule pentane. And I'm going to focus on a specific bond. The bond between carbon 2 and carbon 3. Now, pyrolysis is not specific. Various carbon-hydrogen and carbon-carbon bonds will break, even though we're just looking at one. This breakage is random, so typically pyrolysis reactions are not very useful in the laboratory because it's very difficult to control which bond actually breaks. But you could apply heat, and one of the bonds that could break would be the carbon-carbon bond. And when it breaks homolytically. That is, should be 2 here. You will get radicals. The 2 electrons of the bond split up, 1 electron going with one atom, and the other electron going with the other atom. Now, radicals are reactive intermediates. They do not last long. And radicals can react with species. They usually react via chain reactions, and we'll be looking at chain reactions in detail next semester. But when radicals react, they often generate new radicals. The steps that actually get rid of the radicals are called termination steps. And termination reactions in pyrolysis occur by radicals coming together and coupling to form new bonds. For example, this propyl radical and ethyl radical could join up again and make a pentane. That would be called a coupling reaction. So a termination if you like, and termination means getting rid of radicals, a termination reaction could be a coupling reaction, where two radicals come together and couple. The second type of reaction is disproportionation. Let's write that out. A disproportionation. Disproportionation. Disproportionation reaction is one in which one of the radicals gets oxidized, and one gets reduced. Now, in order to understand this, we have to have a rudimentary understanding of oxidation and reduction. Oxidation can be defined in several different ways. A compound is said to be oxidized if it meets one of the following four conditions. It can lose electrons, so oxidation is accompanied by a loss of electrons. So oxidation can be a loss of electrons from a molecule. A molecule that loses electrons can be said to be oxidized. Or we could calculate an increase in oxidation number. An increase in oxidation number. There could be the more obvious one, the addition of oxygen. Or the removal of hydrogen. Removal or loss of hydrogen. Reduction is just the opposite of this. Reduction is the gain of electrons. It is a decrease in oxidation number. decrease in oxidation number. The loss of oxygen or lastly, the addition of hydrogen. Okay, so if you meet any of these four conditions, depending on the condition met, you are either being oxidized or reduced. How does this apply to disproportionation, to the termination reaction of two radicals? Well, remember, we had a propyl radical. Suppose my propyl radical comes in and reacts with the ethyl radical. So I have this propyl radical, and it's coming in to react with an ethyl radical. So here is my ethyl radical. Instead of coupling, a radical can actually scavenge a hydrogen off of a carbon. I'll use fish hooks to represent the movement of one electron, that is a half-headed arrow. One electron from the carbon-hydrogen bond goes to create the new bond. The other electron stays on carbon. And so what you get is propane and then you get a diradical, a CH2, CH2 diradical. Now this diradical will not last long, and it is possible for carbon to rehybridize to sp squared, place those two electrons in 2p orbitals, and make a side-to-side bond. That is, very quickly, this diradical can go on and become ethene. Ethene. Now, if you remember, I said disproportionation produces a reduced version and an oxidized version of the molecule. Well, we have different numbers of carbons here, so it's difficult to use oxidation number. But I could repeat this same reaction, and instead of using a propyl radical, I can use two ethyl radicals, in which case I would have gotten propane and, instead of propane, I would have gotten ethane and ethene. Now disproportionation reduces one and oxidizes the other. By definition, the addition of hydrogen is reduction. To form ethane, I had to add hydrogen. To form ethene, I had to lose hydrogen. Ethene must be an oxidized version, whereas ethane is a more reduced molecule. It would be nice if I could show this quantitatively, because looking at this, it's pretty easy to see that there was addition or loss of hydrogen and apply whether I have oxidized or reduced my molecule that forms. I can define a term, oxidation number, which is very similar to the definition of formal charge that we've had earlier in this course. Oxidation number is the charge on an atom Now, if you remember the definition of formal charge, it was the charge on an atom assuming equal sharing of electrons. To determine oxidation number, we define oxidation number as the charge on an atom assuming unequal sharing. Assuming unequal sharing. Of electrons, and I'll symbolize electrons as an E negative. Assuming unequal sharing of electrons. That means if you have a structure, say like ethane, if I want to determine an oxidation number for carbon, I take its valence electrons that carbon normally has, which is 4, and I subtract from it the number of electrons it has in bonds, assuming unequal sharing. That is, we assume the more electronegative atom gets all the electrons. Now, for the purposes of this calculation, we assume carbon to be more electronegative than hydrogen. So, if we're calculating the oxidation number, ON, for a CH3, and we have 2 of those here, we take the 4 valence electrons of carbon, and we subtract from it, count the bonds. Well, who's more electronegative, carbon or hydrogen? If carbon was less than electronegative, I would not count any of the electrons. But since carbon's more electronegative, I count both of them. 2, 4, 6. Now, who's more electronegative, carbon or carbon? Well, obviously, they have the same electronegativity, and in that case, you split it down the middle. So you get 1 for the carbon-carbon bond. So that's 2, 4, 6, plus 1, 7. 4 minus 7 equals minus 3. We have 2 of those, so it is times 2. So that gives me my net oxidation number, if you like. Equal to minus 6. So each carbon has a minus 3. Now let's do the same calc for ethene. We'll take the total number of electrons around the carbons, assuming unequal sharing. The oxidation number of a CH2 equals 4 minus, we get 2 for the carbon and hydrogen, 2 for the other carbon and hydrogen, that's 4. 1 for the pi bond, 1 for the sigma bond, that's 4, 6. 4 minus 6 equals minus 2. We have 2 of these, so it's times 2. So my net oxidation number equals minus 4. Each carbon has minus 2. Now the more positive the value, the less negative the value, the more oxidized you are. Ethene has a negative 4. It's more positive than negative 6. Hence, ethene is more oxidized than ethane. Now, you say, why use oxidation number? I mean, it's obvious that ethene has lost hydrogens compared to ethane. That ethene must be a more oxidized version because oxidation corresponds with the removal of hydrogen. Well, sometimes it's not so easy to determine who's more oxidized. Suppose, let's try this guy. Suppose I were to give you something like this. And I was also to draw a molecule that looked like this. And I said, rank these two molecules, A and B, in increasing order of oxidation. That is, start with the less oxidized, the more reduced, and work your way up to the more oxidized. Just looking at the molecules, you might reach different conclusions. For example, you might count hydrogens off of carbon. You might say, well, this guy only has 4 hydrogens off carbon. This guy has 5 hydrogens off carbon. So you might think A is more oxidized. Or, on the other hand, you might say, well, wait a second. This guy only has 2 oxygens on the molecule, whereas this guy has 3 oxygens. He has more oxygens. B is more oxidized. Sometimes when you get molecules, it's not as easily determined just by counting hydrogens or determining number of oxygens. And I'm sure you could build up rules that would allow you to do it. But you already have a set of rules that allow you to determine the oxidation number for the 3 carbons. And long as you're comparing molecules with the same number of carbons, you can determine very quickly who is more oxidized and who is more reduced. If I start with molecule A, I can find the oxidation number for the C double bond O. Okay, so my C double bond O, oxidation number. Carbon. The carbon here has a valency of 4. I subtract from it carbon-oxygen bonds. Who is more electronegative? Well, oxygen is. So, according to our rules of unequal sharing, I cannot count the electrons from the C double bond O. In the case of the carbon-hydrogen bond, carbon is more electronegative, so I can count both of those. That's 2. And the carbon-carbon bond gives this carbon 1. So that's 3. 4 minus 3 is plus 1. We have 2 aldehyde groups that are exactly the same. So if I multiply that by 2, I get plus 2. Now, there is the CH2. The oxidation number for the CH2 equals 4 valence electrons for carbon minus, each carbon hydrogen gives you 2, so there's 2, 4, and then the carbon-carbons give you 1 each, 5, 6. 4 minus 6 is minus 2. Plus 2 added to the minus 2 gives me a net oxidation number for the molecule equal to 0. So what we have is we have plus 1 here, plus 1 here, minus 2 here, and our total is 0. Now let's do the oxidation number over here for the CH2s on molecule B. Oxidation number for CH2. Carbon's more electronegative than hydrogen. I count both carbon-hydrogen bonds. That's 2, 4. The carbon-oxygen bond, oxygen is more electronegative, so I don't count any electrons from that. The carbon-carbon bond gives me 1. So I have 4 minus. And so that's 2, 4 Plus 1 is 5. 4 minus 5 equals minus 1. And there are two CH2s on this that are the same, so times 2 equals minus 2. So each of these CH2s give me a minus 1. Now there's just the oxidation number for the CH. Carbon has 4 valence electrons. The carbon-hydrogen gives me 2. The carbon-oxygen gives me 0. The carbon-carbons, both of them give me 1. That's 4 minus 4 equals 0. My net oxidation number equals minus 2. So 0 for that. B has an oxidation number of minus 2. A has an oxidation number of 0. The more positive I become, the more oxidized I am. So B is less oxidized. And I said, write it down in order of increasing oxidation. So B is less oxidized than A. B is less than A. Okay. Well, it's always good to try problems like this, and I will give you in class some homework problems for you to try. All right. Next, we want to visit or revisit, since we are talking about oxidation, one of the most prevalent radicals found in nature, and that is the oxygen molecule, O2 gas. O2 gas, drawn as a Lewis structure, shows a diamagnetic molecule with all electrons in pairs, lone pairs and bonding pairs. But when we did the molecular orbital energy level diagram, remember sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, star being the antibonding, sigma 2p, pi 2p, pi star 2p, and sigma star 2p. And we added our electrons. Oxygen has 6 valence electrons, but molecular orbital theory uses all the electrons. So we don't use 6 electrons, you use all 8 electrons of the oxygen atom. 2 oxygens, therefore, will have 16 electrons. We follow the Pauli exclusion principle, the Aufbau principle, and Hund's rule in filling orbitals. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Bond order equals the total number of bonding orbitals that are filled. Well, those are the ones that aren't starred. 1, 2, 3, 4, 5. Minus the total anti-bonding orbitals that are filled. We've got 1, sigma 1s star, the sigma 2s star, that's 2. And the pi stars each half filled, so it's 2.5 and 3. 5 minus 3 equals 2. The bond order is 2. The bond order agrees with the Lewis structure, saying there's a double bond. But where they disagree is the molecular orbital energy level diagram described O2 as a paramagnetic structure, a diradical, which cannot easily be drawn as a Lewis structure. If you were to try and draw oxygen as a diradical, it would not be an acceptable Lewis structure. You might have something like this, which suggests the two electrons of the double bond are not coupled. And so the Lewis structure can't adequately show the diradical nature of O2. But O2 is a reactive free radical. Oxygen is what we call a stable diradical. And because of that, it is a selective radical reagent. Using radicals, it can oxidize a wide range of different types of compound. O2 oxidizes C double bond C, allylic, benzoylic, and tertiary H's. The process has several names. It's called oxidation, sometimes it's called air oxidation, or it's called auto-oxidation. In any case, this process is responsible for the degradation of plastics, the breakdown of polymeric compounds, the attack of biochemical molecules in our bodies. In fact, oxygen is so reactive, it's even used by the immune system in what is called the ancillary burst to attack foreign invaders in the body. Let's look at one example. Auto-oxidation of ethers. Diethyl ether can react with air because oxygen can abstract hydrogen off of a carbon next to the oxygen in the ether. Once it abstracts that, it then can couple with the radical that forms. And through a radical reaction, O2 can effectively insert into the carbon-hydrogen bond I've drawn there. So you get an oxygen, and an H. This type of bond, the OOH bond, is referred to as a peroxide. Now what's interesting is when you have combustion, you have to get O2 colliding with carbon to produce CO2. Peroxides already have the O2 attached to the carbon. And because of this, peroxides tend to be explosive. Now, because air has oxygen and this reaction only goes very slowly, it's generally not a problem with ethers. However, if you make a big still of ether, that you boil off and collect the ether. Ether is lower boiling than the peroxide because of hydrogen bonding. That means peroxide molecules concentrate in solution over time as you boil off the ether. So if you boil this ether down, then refill it and boil it down, slowly but surely you will build up the concentration of this hydrogen peroxide version of the ether. Because it's explosive, because you're adding heat, eventually a concentration of this material will get so large that an explosion may result. Because of this, it is important that you never distill ethers to dryness. And often, when you do distill ethers, you add materials that will help inhibit the formation of such species. And these inhibitors actually inhibit radical reactions. Now we're going to talk about radical inhibitors and radical initiators because we want to understand how a radical reaction can be stopped. For example, as in the ether case, we do not want to produce the explosive peroxides. How can we stop radicals? But there are occasions when in the lab you will want to initiate a radical reaction. And you will want to use a radical initiator. So we want to talk now about free radical initiators and inhibitors. So let's start with initiators. Suppose you want to drive a free radical reaction. Suppose I want to do a chlorination reaction. I can take Cl2 and I can hit Cl2 because it's not a very strong bond. I can take Cl2 and react it with heat or ultraviolet light, so I can hit it with that, or I can use Hν to symbolize my ultraviolet light, and I can make 2 chlorine radicals. And then use those chlorine radicals in a radical reaction. But suppose that I have compounds in this reaction that are ultraviolet light sensitive, and they're also heat sensitive. Well, in that case, I have no easy way to produce high concentrations of chlorine radical I need for the reaction. Radical initiators can be used because they form radicals at lower temperatures than it would take to make chlorine radical. These tend to be molecules that are organic peroxides. Organic peroxides. Molecules that are either R, O, 2 lone pairs here, O, 2 lone pairs, R, where R is an alkyl group, methyl ethyl, or R, O, lone pair, O, lone pair, H. Hydrogen peroxides. 2 examples are let's put some dots in so you can easily see the carbons of the benzene ring. 6 carbons. This molecule is called benzoyl peroxide, and you are responsible for that name. We can put it in lone pairs. Benzoyl peroxide. If you heat benzoyl peroxide, it very easily falls apart to 2 benzoyl oxy radicals. What you might call benzoate radical. The bond breaks. What's interesting is the amount of heat required is much lower than required for other typical radical reactions because the oxygen-oxygen single bond is one of the weakest bonds there is. Another molecule is based on this molecule. Can you name this guy? Dots for my carbons of my aromatic ring again. Well, this is benzoic acid. We're going to add an oxygen. Couple oxygens. Benzoic acid becomes, when you add an extra peroxy linkage, peroxybenzoic acid. Peroxybenzoic acid, when heated, produces the benzoate radical plus a hydroxyl radical. Both of these types of radicals that form can be used to initiate a reaction. How? Well, once the radical is formed, if I have Cl2 and I've formed my benzoate radical, the lone electron on the oxygen can scavenge a chlorine, a Cl dot. If it does so, get a benzoyl oxychloride, plus a Cl dot. So this radical can induce the chlorine to fall apart, become this oxychlorine derivative, and you get the chlorine radical you need for your reaction. Radical initiators can be used to initiate radicals. Well, what about inhibitors? Inhibitors are very important in society. They're used in plastics. They are used in most organic-based materials. They're also used in biological systems. Alpha tocopherol, for example, which you should be familiar with, better known as vitamin E, is a major antioxidant used in the human body. Many free radical inhibitors are based on the molecule phenol. The reason for this is phenol has a unique ability. I'll put dots for the carbons again so it's easy to see. When it reacts with some kind of radical, say there is an RO dot. The RO dot will scavenge the hydrogen, making ROH, and you will produce phenoxy radical. The interesting thing about this phenoxy radical is that it is resonance stabilized. I can move pi electrons with fishhook arrows where the electrons of the pi bond here are splitting up. Joins the radical, makes a new pi bond here, putting the dot in this position. And if we continue doing that process, we can move the dot right around the ring. So if I continue with this, draw a larger one. When I'm finished moving this right around the ring, I'm back to an O dot. But resonance like this stabilizes the radical. The radical is not isolated in any one position. It's said to be delocalized around the ring. Remember, none of these individual resonance structures exists. What exists is the resonance hybrid. The resonance hybrid would look something like this, if you like. Where the lone electron, delta dot, appears in these positions. And the pi bonds, if you like, are delocalized. Let's use dashes instead of dots, it'll get confusing. Delocalized around the ring to these positions. And so this radical, based on phenol, is much more stable, longer lived, less reactive, less likely to attack things, perhaps available to be metabolized and disposed of biologically. Slowing down in plastics, radical breakdown of carbon-carbon double bonds, and so your plastics don't become brittle and crack. Your food materials don't break down as rapidly. By adding such preservatives to cereals, the cereal retains its integrity, doesn't break down and turn to dust as quickly. A common preservative used in foods, for example, was this molecule. A phenol with what kind of groups around the OH? This molecule. Let's find its IUPAC name. Well, I see two potential aromatic base. Longest carbon chain certainly is the 6 carbons of the aromatic ring, making it a benzene. There is a special name for a methylbenzene called toluene. A hydroxybenzene is called a phenol. What do we name it as under IUPAC? Well, phenol is higher priority. OH is a higher priority group than methyl, so phenol gets the root. As soon as you say the word phenol, you must number from the hydroxy as number 1. And so if I proceed around the ring, 2, 3, 4, the methyl's 4, 5, 6, and the tert-butyl's at 2. So the IUPAC name is 2,6-di-tert-butyl. 4-methyl, and you could say 1-phenol, but since phenol has to have the OH as number 1, it is sufficient to just say phenol. The name under which this chemical was marketed was referring to tert-butyls as butylated. The OH is hydroxy. The marketed name, or common name, was butylated hydroxy toluene. Butylated hydroxy toluene. Butylated hydroxy toluene had the short form BHT. So a short form term BHT was given. Why was butylated hydroxy toluene an excellent food preservative, an excellent radical inhibitor? Well, as we've seen, the phenol group would be resonance stabilized if it picked up a radical. And hence, the delocalization of the lone electron would stabilize it. But more than that were these bulky tert-butyl groups. They're so bulky that they block off access to the OH, so that once the H is removed, the O radical that forms is protected. It would be very hard for something to get by these tert-butyl groups and react with the oxygen radical. So a steric effect also aided the stabilization. If you like, you could say steric hindrance of the tert-butyl groups, or steric hindrance caused by the tert-butyl groups, prevented attack of the oxygen radical. Add that to the resonance, and this makes BHT a far more effective radical inhibitor. Okay. The next radical reaction we're going to look at is the organometallic reaction. We're going to take a look at organometallic compounds. And the reason we're going to look at organometallic compounds in this section is because organometallic compounds form via a free radical mechanism. Now, organometallics of the type we're looking at are compounds in which carbon is bonded directly to a metal. Carbon is bonded directly to a metal. Now, there are several examples of these. First one I'm going to draw is this molecule. A butyl group. See if I can find this. This molecule is named as an alkyl lithium reagent. Its name is butyl lithium. All one word. You can also have such alkyl groups attached to magnesium. Here we have an alkyl magnesium, an ethyl magnesium. And you can have any halide as the other ion. You can have a bromine, a chlorine, an iodine. So it could be ethyl magnesium bromide, ethyl magnesium chloride. This is a bromide. The bromide is a separate word. Ethyl magnesium bromide. The magnesium reagent is referred to as a Grignard reagent. Now these types of compounds, both the Grignard reagent and the alkyl lithiums, are formed by taking alkyl halides and stirring them in the presence of the metal. For example, I take ethyl bromide and I stir it up with some magnesium metal. It's an exothermic reaction, so we boil off ether to take the heat away. Diethyl ether is our solvent. And we produce the ethyl magnesium bromide. It is a radical reaction in which the magnesium metal actually inserts into the magnesium bromine, the carbon-bromine bond. Likewise, you can form butyl lithium by taking butyl bromide and reacting it with two lithiums. The two lithiums, well, let's show that. So let's show R to represent my butyl group. I can use chloride bromide, but let's use bromide. R bromide reacted with two lithiums. The two electrons available from lithium, each lithium wants to lose one electron. those 2 electrons go into the anti-bonding levels of the carbon-bromine bond. And you also usually do this in some kind of ether solvent. And the extra 2 electrons, make the R- group, so you get your alkyllithium, your RLi, where R is minus, Li is plus, and you get lithium bromide, Br minus. So you can form these types of compounds by reaction in ether with the free metal. Now, Grignards are not stable on their own. Grignard reagents, where X is some halide, R is an alkyl group, require ether solvent. You do not isolate them. The Grignards in solid form would be explosive, extremely reactive, and dangerous to isolate. But the ethers help stabilize them. The solvent, ether, solvates the magnesium with its lone pair of electrons and dumps electrons, if we use diethyl ether as I'm showing here. Diethyl ether is one of the most common ethers, being known to have been used since the 1500s, is often just referred to as ether. The lone pair of electrons dump electron density into the empty 3d orbitals. Of the magnesium, helping to stabilize. Okay, they help to stabilize the Grignards. Grignard reagents are unstable unless solvated by ether. Okay, how do Grignards and lithium reagents react? Well, Grignard and lithium reagents, organometallic compounds, the metal is more electropositive than carbon, which is fairly rare. In other words, carbon's more electronegative than the metal. So the delta plus is on the metal and the delta minus is on carbon. Previously in our nucleophilicity discussions, we listed across a period that CH3 minus is a stronger nucleophile than NH2 minus, who's a stronger nucleophile than OH minus, as a general trend, who's stronger than F minus. But we never explained how you could form CH3 minus. How on earth do you pull a proton off of a carbon atom? Carbon not being electronegative at all. The very fact that CH3 minus is such a powerful base, such a supernucleophile, makes it unlikely that you could form it in the first place. Well, it turns out that these organometallic compounds act as nucleophilic carbon, basic carbon, C minus. And so they can be used as a source of C minus. For example, let's start with a very simple aldehyde. This molecule is methanal. Oxygen's more electronegative than carbon. So there's a delta minus here and a delta plus. I can react this with ethyl magnesium bromide. Now, when I write ethyl magnesium bromide, I usually understand it's dissolved in ether. And sometimes you'll see ether written there. I will also add H3O plus after the reaction's completed. That is what this 1 and 2 out front mean. 1 and 2 means first react with ethyl magnesium bromide, then react with acid. Now, we have to be sure when we do our reaction, so let's show each separate step. when we do our reaction with ethyl magnesium bromide, that there is no protons on electronegative atoms. There's no source of H+, because ethyl minus will grab an H+ before it acts as a nucleophile. If there's any H+ around, that is any H on an oxygen, or H on a nitrogen, or H on a fluorine, or H on a chlorine, this CH3-CH2 minus will pull the H+ off of those electronegative atoms and make ethane gas, and you will not get a reaction. So we don't want anything like that around. So you have to make sure your ether is absolutely dry, that there's no water in it, because H2O would protonate this ethyl minus and make ethane gas, and ethane gas would just bubble out of solution. But if there is no positive charge H to go for, then the C minus can act as a nucleophile and attack the positive delta plus on the carbon here. Okay? And if it does, that would create 5 bonds to carbon, so we can't have that. So the pi bond shifts out to this oxygen. And what I end up with, of course, is 3 lone pairs around the oxygen, a negative charge, my H, and the ethyl group bound here. Okay. Now, closely associated with the O minus, of course, will be the MgBr+. Now, you don't have to draw it. You know it's there. When you add the H3O+, the H3O+ will protonate the oxygen and dissolve the magnesium solvent in the magnesium salts in the H2O solvent. And so you end up with your final product, propanol. So if you add a Grignard to formaldehyde or methanal, you produce a primary alcohol. Now, Grignards can be made from any kind of alkyl or aryl halide. You can use bromobenzene to make phenol magnesium bromide. You can make ethyl magnesium bromide. You can make all kinds of Grignards. And in each case, ethyl puts an ethyl group here. Methyl magnesium bromide would put a methyl. If I use phenol magnesium bromide, I would have put a benzene group there, phenol group. I got this guy because this came from the aldehyde, methanal, and this came from the Grignard. Let's try with a different aldehyde. Let's try ethanal. What happens if I take ethanal? And react ethanal? Let's try a different Grignard. Let's use phenol magnesium bromide. So we're going to hit it with phenol magnesium bromide. I'll draw dots so you can see the carbons. There are 6 carbons. This is a benzene ring. Phenol magnesium bromide in ether. Second step, we add H3O+. If the 1 and 2 were not there, you would be saying you'd throw acid in with the phenol magnesium bromide. That would just put H+ on the phenol minus. H+ and phenol minus makes benzene. The 1 means react the phenol magnesium bromide first with the ethanal. Let's show what that would form. phenylmagnesium bromide. There's a delta minus here. So delta plus on carbon. The phenol goes for the delta plus. Pi electrons go out on oxygen. So we don't get pentavalent, and we have a CH3. We get our C, an H, an O minus, and then you have your phenyl ring. Carbon, 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 carbon. This immediately can react with the H3O plus once it's added, which will protonate. So H3O plus simply puts a proton. What's interesting, note, is all other aldehydes other than formaldehyde or methanal, molecules like ethanal, give you secondary alcohols. And so we put a phenol on. So there is my phenol. And we produce a secondary alcohol. So all other aldehydes give us secondary alcohols. What happens if I react with a ketone? Well, let's try this molecule. Can you name this molecule? Its common name is diphenyl ketone. I've got two phenols. I'll put dots for the carbon so you can be sure there's 6. The circle in the middle just means delocalization. You can draw your aromatic rings with either pi bonds or a circle like this. What is the IUPAC name of this? It is benzophenone. Remember that. Benzophenone. Benzophenone reacts with Grignard. Let's hit it with, how about methyl magnesium? Let's change it this time. We could make it from methyl iodide, which would make methyl magnesium iodide. It is also a Grignard reagent. Hit it with H3O plus in the second step. What will that produce? Well, the methyl magnesium iodide. Magnesium's electropositive, so there's a delta minus on the carbon. The delta plus on the carbon here is caused by the electronegative oxygen, so the CH3 will attack that carbon. Pi electrons will move out. Let's use pi bonds this time. Means the same thing. And the CH3 goes on. Usually when you have a molecule like this, if you use a circle, make both the circles. If you show the pi bond, show the pi bond. And of course, there's probably an MGBR associated here. You could show it. You don't have to. I'm not going to require that, but if you want to, you can. And then the H3O plus will add, once you throw it in the second step. And that will protonate. And you will get diphenyl ethanol. 1,1-diphenyl ethanol. There you go. By way of reaction, a very interesting reaction is what will happen if you take a Grignard with CO2. For example, what if I take benzoyl bromide react it with magnesium metal and make benzoyl magnesium bromide. And then I hit that with, I bubble in CO2 gas. Or I throw in chunks of CO2 as dry ice in solid form, where it converts the gas and bubbles through a solution in ether. And then in the second step later I add H3O+. What's going to happen with CO2 gas? Well, if you draw out CO2, you know CO2 has two oxygens bound to carbon, where carbon's sp hybridized and the oxygens are attached through double bonds. The oxygens are electronegative, delta minus, and so there's a large delta plus on the carbon. In the Grignard, the delta plus is on the magnesium. There's a delta minus on this benzoyl group. So the carbon's going to be attracted, of the benzoyl group, is going to be attracted to the delta plus on the carbon dioxide. Of course, that would create 5 bonds of carbon. You can't have that. So pi electrons move out to the oxygen. And what you end up with, when you're done, is a CH2 attached to a C double bond O and a single bond O, which is negatively charged. You've made a carboxylate. And of course your MgBr plus is here as well. Now, once you throw in the H3O+, you protonate and make carboxylic acid. So CO2 gas added to a Grignard reagent will produce a carboxylic acid. Now what's interesting about all of these reactions is I could have replaced the Grignard reagent with the Alkyllithium reagent and have produced the exact same reaction. Of course, instead of having Mg here, instead of having magnesium bromide plus with the ion, I would have had lithium plus if I had used benzyl lithium in this reaction. And the alkylithiums behave just the same as the Grignard reagents. So all of these reactions I've shown would have worked for alkylithium reagents. Well, if these reagents are powerful nucleophiles, can we say do an alkyl halide reaction? Can we, for example, take CH3, CH2, CH2, primary alkyl halide like that, hit it with something like methyl magnesium bromide, and have the delta minus of the organometallic attack the delta plus on the carbon with the iodine and do an SN2? Well, it is important you understand that the alkylating agents, the Grignard reagents, methyl magnesium bromide or methyl lithium, are extremely powerful. And sometimes when you attempt reactions, they're so powerfully reducing, they transfer electrons rather than attack. And when you react them, you don't sometimes isolate the products you expect. These alkylating reagents are so powerful, this reaction does not work well. And what we have to do is attempt to lower the reactivity, if we can, lower the reactivity of these reagents. And one way to do that is to prepare the alkyllithium reagent. As I stated, you can take methyl bromide, react it with 2 lithiums, and produce methyl lithium plus lithium bromide. And methyl lithium is a very powerful alkylating agent, similar to Grignard. But what's interesting is I then can take 2 methyl lithiums and react it with cuprous iodide. Now copper has a 1+ charge, and the 2 methyl minuses will add to the copper. That will produce dimethyl cuprate, because copper is +1, 2 methyl minuses added. That means this whole thing has a negative charge, and so we need a lithium. Now you're responsible for being able to name these. Lithium is a separate word out front, and all you do is name the alkyl group. In this case it's methyl, so it's dimethyl, and the dialkyl cuprate is one word. So cuprate is for a negatively charged copper. Yes, copper is a +1, but by the time you add 2 methyls, the total charge on it as a whole is negative. So lithium dimethyl cuprate. These dialkyl copper reagents are milder reagents. If you use lithium dimethyl cuprate on this reaction instead of a Grignard, you will successfully cause the SN2 to occur. And if a CH3- knocks out the I, you will get butane. A nice way to make an alkane from an alkyl halide. Now, of course, all the rules for SN2 apply. The alkyl group here must be primary, secondary, methyl. Okay. For the dialkyl coppers, you can use any alkyl lithium agent to make the cuprate, which, such as methyl, primary, secondary. You can't get tertiaries around that copper. It's too bulky. And you can also do it with the aromatic phenol, vinyl. You can do it with those. So a nice way to carry out an SN2 reaction on an alkyl halide and produce an alkane. Now, the last thing we need to re-emphasize is that you do not want any acidic hydrogens around. If you have a CH3 magnesium bromide around, and there is any HN, HO, in fact, you can't even have an H off a C triple bond. That's acidic enough. This guy's so powerful, he'll even deprotonate that. And what will happen if there's an H there and you have that, you will get methane gas. Now, you don't do this unless you actually want an N-, an O-, or a C, for example, a C, triple bond C, lone pair here, which is called an acetylide ion. If you have an H on any of these, it will quench a reaction, and students often miss this on quizzes. For example, suppose I gave you this aldehyde. And I said, let's react it first with methyl magnesium bromide in ether. I'll write it out this time. Often you say ether after a slash to indicate solvent. And then 2, you hit it with H3O+. Well, as usual, the methyl minus will attack the carbonyl. This will move the pi electrons, and then the acid will protonate it. So the product is an OH with a CH3 that came from the Grignard. But if I gave you the same reaction with the same aldehyde, but in this case there was an OH here, and I hit it 1 methyl magnesium bromide in ether. I'm not going to write the ether this time. And then H3O+. A lot of students would draw the product saying, okay, well, yeah, we got the HO, CH2, CH2. The OH will go here and the methyl will have added, just like the one above. But in this case, that's wrong. Why is that? Methyl minus would have grabbed the proton off the alcohol first. When the Grignard attacked, it would have grabbed that proton, making methane gas. The methane gas, I'll use an arrow up, meaning to bubble out of solution. Methane gas would bubble out of solution, and you'd get OCH2, CH2, and your aldehyde unaffected. The Grignard grabbed the proton. It did not attack the carbon, and you'd have 3 lone pairs around the oxygen and a negative charge. And what happens? What happens when you add H3O+ then? Well, the H3O+ will just protonate the alcohol. And you'll get back, look what you get back. You get back the starting material unaffected. What happened to your Grignard? Where did it go? Why didn't it attack the aldehyde? Because it's a powerful base first. If there's an H on an electronegative atom, it grabs the H+, becomes methane gas, and bubbles out of solution. When you add the acid, the magnesium salts dissolve, and it looks like your aldehyde did no reaction. So beware the presence of H's on electronegative atoms or H's on alkynes. Well, there you have it. I'm Dr. Brian Lloyd, and this is my Scribblecast. This is the end of a free radical section. We've looked at a lot of material. Free radicals, oxygen, free radical initiators and inhibitors, and organometallic reactions. In our next lecture, we'll be examining alcohols and their reactivity. Thank you very much.